Okay, so this is going to be a follow-up video to the last video that I made on tensors. Um, so the last video was a introduction to what a tensor is, where they come from, how they're really not that complicated. Um, this video is going to be more on how to use them for practical purposes. Okay, so I'm calling it a practical introduction to tensor calculus using Einsteinian index notation. So Einsteinian index notation is what you're going to see in physical applications, and by a practical introduction I mean I'm going to be skipping a lot of the very heavy, difficult mathematical theory and just getting down into the special cases that we use for physical sciences. Okay. This is basically pretty much all the information that you need to start using tensor calculus for physical applications. And I'll just say that if you're a member of the computational fluid dynamics master's degree course, I'd say you may have guessed at this stage that I am also a member of the course who would wish to remain anonymous. So I'm making this video because I think it will potentially really help other people in this MSc. Okay, let's get started. So the first question we should probably ask ourselves is why even bother, right? We have all these really complicated mathematical ideas, you know what I mean? And is it really worth all of this, really head-wrecking difficult stuff to get these calculation tools? And I argued that it is worth it. It is indeed worth it. Okay, let's see why. So the first major point is coordinate flexibility, right? So in an introductory vector calculus course, you might see them define the Laplacian as basically the sum of these three, the second derivatives of the three variables. You take the sum of those. Okay, that's your first year definition. But this definition really depends on the coordinate system that we're using. What if we want to talk about R3 in a different way, right? And the relevance of this, right, is so we have Gauss's law in electrostatics that the Laplacian of the electrical potential is the negative charge density over the electric permittivity, okay? But we only know the definition of this Laplacian in these standard coordinates. So we ask ourselves, what does this equation look like in some other coordinate system? Or indeed in some other space? What if it's not R3? What if we're working in some curved surface, or space? Is it even true? Is it even true? With this definition of the Laplacian, it's not even true if it's true in another space or coordinate system. We feel gutturally that the answer should be yes. It should be true, because physics shouldn't care what coordinate system that we choose to use. But it's not immediately clear. That's the point. Okay. The second main reason is ease of calculation. So, example exercise, show for a differentiable, well, twice differentiable is what that should read there. That really should read twice differentiable. Okay, but whatever. From R3 to R3, show that the divergence of the curl of it is 0. Well, if you're doing it the first year way, first you got to calculate the curl, which is already some bothersome, determinant. Ux, Uy, Uz, You know, do all this nonsense, and then you got to take the divergence of this thing, and you got to say, oh, okay, this term is this term, and this term is the same as this term, and this one, and we get 0 as expected, right? But we just did this calculation in our standard x, y, z coordinates. You know, is it true in another coordinate system? We're not sure. Okay, so not only is the calculation longer, okay, but it's also potentially unclear if it generalizes. So once you get into tensor calculus, you'll start doing this the expert way, okay, which is, boom, look at that. It's one line, first of all, and it is clear once you're experienced with this kind of thing that this thing is indeed a proper scalar, and so it transforms in some predictable way to other coordinate systems, and so the whole thing generalizes. We'll see what we mean by this later. Okay? So before we start really getting into tensor calculus, we have to take a brief foray into differential geometry and Riemannian manifolds. First question, what is a manifold? Okay, here I wrote smoothly. Okay, smoothly. That's actually not required. A manifold doesn't have to be smooth, but the manifolds we're going to be seeing in physics. Physics deals with smooth manifolds. Okay, so that's fine. But the key words here are simply connected space. And again, these have some rigorous mathematical definitions that are really not relevant to us. Simply connected is basically as good as you need. So for example, you know, a line is a manifold, the plane is a manifold. In fact, any Rn with n in the natural numbers, that thing's a manifold. It's actually known as the trivial manifold. Okay, what else is a manifold? The circle is a manifold, the disk is a manifold, this blob is a manifold. Okay, what are not manifolds? Things like this cross, because it has this intersection, this self-intersection. Infinitely detailed objects like the Sierpinski triangle, you know, it has this infinite detail. It's also not a manifold. Okay, fractals and self-intersecting shapes. Okay, but all of the nice stuff that we're going to do physics on, they're all manifolds. Okay, so now we're going to talk about the metric tensor. So basically, when you have a manifold, okay, you have some manifold, okay, you can take a point on the manifold, and there's a thing around that point called the tangent space. And it turns out that this thing is actually a vector space. Okay? And we know that if we have a vector space V, we can define dual space V star, and then from these two guys, we can start to talk about tensors. Okay? So what is a metric tensor? I say a metric tensor because it's not unique. Okay? Symmetric, non-degenerate, 0-2 tensor. So let's unpack what this means. So this, again, from our previous video, basically means bilinear map. Okay? This part right here, non-degenerate, means that G of something with itself, so G is the symbol that's typically used, is greater than or equal to 0. And symmetric means G of xy is equal to G of yx. Okay. So these gives us the notion of distance, oh, whoops, wrong word. Notion of distance and angle on the tangent space in a manifold. It is defined as basically the inner product, GUV equals the inner product of U and V in some precise sense. And then we can expand that into the basis elements like this. So if GUV is inner product UV, then GIJ is just G of EI EJ, okay, which is the inner product of EI and EJ. So this might seem a bit circular, and I'm defining the inner product with the metric tensor and defining the components of the metric with the inner product. But basically this just underlines the fact that the metric tensor is not unique, but typically we have some sensible way of choosing which one it should be, right? So for example, if we're in R2, okay, if we're in R2 and we want to talk about, we have our basis vectors here, we have E1 and E2, okay, whatever metric tensor we choose, it better tell us that G11, which is equal to G of E1, better be 1, because we know physically the length of this guy is 1. And it also should tell us that G12, which is equal to G21, better be 0, because we know that the inner product of E2 and E1 is 0, right? Because these guys are perpendicular, okay? Just from physical intuition, right? So whatever way we choose our metric, it better give us these two, all right? And that's actually enough to pin it down uniquely. So now, if M is a manifold with a metric tensor G, then this thing right here, this pair, is called a Riemannian manifold. So a Riemannian manifold is basically a manifold that we can measure distances on and do calculus on. All right. So cool things you can do with the metric tensor, okay, you can do this stuff called index gymnastics, okay. So if I have a U, which is in our original vector space, okay, then U has components, UI, upper indices, okay. What I can actually do is if I define an object W having components W I is equal to G I K U K, then this W is actually a covector, right? So we started with this U, which is a 1, 0 tensor, and we were able to construct this thing here, which is a 0, 1 tensor, right? So that's pretty cool. So we have this U, okay, which is an element of our original space, and we map it to, in the business, it's actually called the flat, okay, which is in the dual space, all right? And if you're interested in what I mean by this flat, Google musical isomorphism, if you're curious about the details, but they're not that important. And the other way around is also true, right? So if I take this W that's in this dual space, I can actually map it over to, it's actually called the sharp, which is in our original space, and it's very similar, okay? But this time I use the inverse metric. So now GIK WK equals, say, UI, which is now a 1, 0 tensor. And this inverse metric, its components satisfy this law, okay, where this delta ij, as a reminder, is 1 if I equals j and 0 if not. And if you write this in a matrix form, you basically get G times G minus 1 equals the identity matrix. So this thing can basically just be found using matrix inversion. Now, you have to be careful when you talk about matrices, because a matrix is formally a 1-1 tensor, whereas G is a 0-2. But from a computational standpoint, they're the same thing. Okay, and the beauty of this now is that we can basically say U super K V sub K, this summation here, is actually the same if we switch the position of the indices, right? We can actually switch up and down summing indices, because we can write our index raising and lowering, and then we have this guy here, and that's going to be a delta ij here, and then we say, we'll just set j equal to I, and then I is a dummy, so you can switch the symbol to whatever you want, ukvk, and we get this index switching ability. So that's pretty cool. All right, next thing is connection coefficients. So this is some quite technical mathematical theory. Basically, if we have a smooth manifold, M, we can basically give it this thing that we call a connection, which is this nabla, okay? And this allows us basically to, before all of these tangent spaces on different parts of the manifold, these were all kind of separate, but with the connection, we can basically link them together in a very precise kind of way that is not important to this video, okay? And actually, you don't need a metric, okay? So you don't even need to be able to measure distances to be able to do this in a sensible way. So in pure math, okay, you can build the connection without the metric, okay? But in applied math and physics, all of the manifolds we deal with come equipped with a metric, and from this we can build the connection in a unique, sensible way. So in the same way that the metric was not unique, the connection is also not unique, okay? But there is a unique, if we have a metric, there is a unique sensible choice, okay, for the connection, all right? And once we have that connection, we can define these things called the connection coefficients, these gammas, also called Christoffel symbols, all right? And they basically measure how much the angle between basis vectors changes, okay? So if we choose the sensible metric and a sensible connection, again, in some precise kind of way that's not relevant to this video, we end up with this formula here. Whoops. We end up with this formula here, okay? And the derivation of this formula, again, is not relevant to this video, but this is a very important formula and worth writing down, okay? So we can build our connection coefficients from our metric, okay? And basically what this equation here means is that if I have a manifold with these, you know, coordinate lines on them that can be all kind of curvy and straight or curved the other way, right? Basically, here, for instance, you know, here, for instance, the basis vectors make this angle. Here they make this sharper angle, okay? So the angle between the basis vectors isn't the same, but the way that it changes between these points is going to be described by our connection coefficients, okay? Our connection. A lot of mathematical theory here, but it'll become clear in a second, okay? All right, so tensor calculus on manifolds. Let's get into it. So the point is that regular derivatives are just not good enough, okay? So if I have some vector u, okay, which has components ui, is this thing, I'll call, let's say, a, I, j, which is the derivative with respect to the jth coordinate of the ith coordinate of u, is this thing a tensor? And it turns out, no. No, it is not a tensor, okay? We actually need something else, okay? Because if I take the derivative with respect to the jth coordinate of the whole vector u, and I take the ith component of that, then that thing is a tensor, okay? But what you'll get here is that this is going to be the jth derivative of the ith coordinate, but you're going to get plus some other stuff, okay? And this is, we can show that this is definitely not a tensor, okay? And if we have a tensor as the sum of not a tensor and something else, then this thing also can't be a tensor, okay? Because you can't add tensor with not tensor and get a tensor, okay? But you can have not tensor, let's say not t for short, plus not tensor and get a tensor, okay? It's possible to do that, all right? And this stuff, you'll notice that if we do dj of u, and I take the ith components of that, well, let's forget about the ith component for a second. The derivative with respect to the jth coordinate of u is going to be, well, we have to write u as the sum of its components with basis vectors. So then this is going to be ek dj uk plus uk dj ek, and you'll notice that this derivative of this basis vector, okay, this is related to these connection coefficients that we had before, okay? All right. So what this leads us to is a thing called the covariant derivative, okay? So the covariant derivative of a PQ tensor is a PQ plus 1 tensor. So hence the name covariant derivative, because it basically adds, ooh, boy, oh boy, that's a big one. It adds a covariant index, essentially, okay? It's linear, and it also obeys a product rule. So what do I mean by that? Okay, so again, the tensor, the covariant derivative of a tensor is also a tensor, all right? And what I'm saying by the product rule is that the covariant derivative of S, tensor product T, is S, tensor product del T, plus T, tensor product del S. Okay, so we have this product rule here. And the indices of the covariant derivative are given by these expressions here. Okay, and you'll notice that this was basically, you know, when we had the, you know, when we had this thing here, we ended up getting this, you know, dj, this ek dj uk plus uk, you know, and then something involving the gammas, okay? And that's basically what we have here, okay? And the rule is that you add for upper indices, you add, and for lower indices, you subtract. And then you can actually do this as many times as you want. So this is a 1, 0 tensor, this is a 0, 1. This is going to be the covariant derivative of a 1, 1 tensor. Okay, let's use a different color. So you subtract for this one, and you add for this one. And then you can add on as many terms as you want, right? So if we had like an m here, okay, put an m here, put an m here, put an m here, and then we would just have another term where it would be gamma L, let's see, L, oh, I'm losing my marbles here. Yeah, L, M, J, A, I, J, M. Oh God, I'm completely losing my marbles. Yeah, all right, whatever. The point is, you can keep adding and subtracting as many terms as you want to get the covariant derivative of, you know, a tensor of any, you know, of any shape that you want. Okay, that's the point there. Okay, and now the other neat part about the covariant derivative is that it's also metric compatible. Oh, I should mention first. So you can show that these indeed transform as tensors. And the other neat thing is that it's compatible with the metric. So the covariant derivative of the metric is 0. Okay, so this makes the calculations fairly intuitive, right? So again, we had this index switching property, right? We had UKVK equals UKVK, okay? And we can do similar with these differential operators now, right? Because, you know, we can write the index raising formula there, and then we use our product rule that we established. So we get this and this, right? But this is the covariant derivative of the metric, all right? So this guy is 0, so we just get this guy. So del lower u upper is equal to del upper u lower, so it's the same thing. So what all of this means basically is that in a very correct and formal sense, this del is a 0, 1 tensor in a very correct way, okay? So we can write our, you know, vector calculus differential operators in terms of this del, right? So this is quite cool. So now, you know, remember in the past, right, we were using our first year definitions. We had this grad is equal to like d dx, d dy, d dz, but again, this is only in one coordinate system, but here, this, you can use this in any coordinate system you want, right? So if I want to take the gradient of a scalar and get a vector, I need to be careful because this del, this is a 0, 1, but a vector is a 1, 0, all right? But that's an easy fix, right? All I need to do is take this phi, this del phi, which is covariant, and all I need to do is just index raise it, okay? So the gradient is just the index raised version of the covariant derivative, okay? The divergence of u is basically just the inner product of the covariant derivative with the entries of the vector, okay? And the curl is this thing right here, where this guy, okay, is the Levi-Civita, ooh, I totally botched that, tensor, not the same as the Levi-Civita symbol, but the two are closely related. All right. They're quite close. You can look that up in your own time. And again, all of these quantities transform in tensorial way. We can define the Laplacian as basically the trace of the double covariant derivative. So actually, we have the Laplacian operator is defined as the trace of the double covariant derivative, okay? But this thing, again, I said that this guy was formally a tensor, and we know that a tensor, a 1, 0 contracted with a 0, 1 is a scalar, right? Because, you know, this thing is going to end up being a 0, 0 tensor, so this thing is a 0, 0 tensor operator. So basically our Laplacian is a scalar operator. All right, so the Laplacian of a PQ tensor is a PQ tensor, another different PQ tensor. All right, because a scalar times a tensor is a tensor. All right, so that's quite cool. So the Laplacian preserves the shape of a tensor. And then finally, we can make directional derivatives. Okay, so this du is equal to ui del I. So this is important. We have, right, del k uk is not the same as uk del k. Okay, right, because this thing is a proper scalar, whereas this thing is a scalar operator. So not the same thing. Okay. But these are some important and very useful definitions, because again, what I'm trying to underline here is that all of these are basically coordinate-free descriptions. Well, they're not completely coordinate-free, but you get the idea. So some example usage. So the first thing is, if you're familiar with a bit of, you know, tensor language and some common mathematical syntax that you'll probably learn if you go on with this subject, you can write things in a very simple way. So we had this rate of strain tensor, which was the symmetric part of the velocity gradient. Okay, so again, we were able to, if you remember, we were able to take this velocity gradient, which again, this thing is a tensor because u is a vector, and a vector is a tensor, and the covariant derivative of a tensor is a tensor. So this whole thing is a tensor, so that's good. All right, we were able to decompose that into a symmetric part and a anti-symmetric part, which I'm not sure if the symbol is all that agreed upon, but I guess I'll use omega. Okay, and then this guy was, you know, 1/2 del u plus del u transpose, and this other thing was the same but with a minus sign. But that's a lot of writing. So actually what you can do instead is you can use this abbreviation, which is a nice way of writing it. So you can write del u ij is equal to del u parentheses ij plus del u brackets ij. This is called the symmetric part, and this is the anti-symmetric part. All right, it just makes it, we can write things really shorter, all right, which is nice. Okay, but that's not the main power of this. The other great thing is calculation shortcuts, all right? So show that if u is divergence free, that the directional derivative of u in the direction of itself is the same as the divergence of its tensor product with itself. Now, if you were doing this without this index notation and knowledge of tensors and so on and so forth, this would be a real pain in the butt, okay? Because it would be very tedious, because this one you'd have to write as this, you know, ux d dx plus uy d dy plus uz d dz. And then you got to write the vector ux, uy, uz. And then the other one, you got to calculate u tensor product u. So you got to go, oh god, ux, uy, ux, uz, and do 3 more rows, and then take the divergence of that thing. It's just a pain. It's a ton of writing, okay? But if we know some tensor calculus, then this is the definition of the directional derivative, and then we know u tensor product u ij equals ui uj. Okay, we plug that in, contract on this index, we get this term and this term for our product rule. We recognize the divergence. That thing is going to be 0, and so just this term survives, and voila, we get the same thing in both cases. Okay, so that's beautiful. Saves us a ton of writing. And not only that, I've been talking about this before, this is coordinate independent. Independent. So we can use x, y, and z, or Cartesians, or we can use whatever coordinate system we want, and this is always true, because we've shown that it transforms in a tensorial way. All right. And this is the main point. You can work in other coordinate systems, right? So if I'm working in R2, for instance, we have our position vector is going to be, x1, x2, and we introduce the coordinate transformation for polar coordinates. This is r cosine theta, r sine theta, and then grr equals dx dr dot dx dr, which you can check is 1, and similarly g theta theta is equal to, blah 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 theta, blah 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 theta, and you can check that that's r squared. Okay, so you get this is the metric tensor. All right, and then from that formula, that very important formula before, we are able to work out the Christoffel symbols. And then from the Christoffel symbols, we are able to build our covariant derivatives, right? And from that, we can, for instance, very quickly get a formula for the divergence, okay? But I must warn you, okay, that we need to be careful with bases. Holonomic versus normalized bases, right? Because what you'll notice is that this formula is actually different than the one you'll see in vector calculus books, because in vector calculus books, you'll have the same thing, but you'll have this 1 over r in here, all right? And the reason for that is in differential geometry, okay, we define the basis vector, okay, as the derivative of the position vector with respect to that coordinate. However, in, physics and vector calculus and stuff, we define the basis vectors as this thing, but normalized. So it's actually dx dxi divided by the length of that. Okay, so this discrepancy here just comes down to what you're defining u theta as. Okay, so whether you're defining this component with respect to the holonomic or the normalized basis. All right. So it's not hard to fix, but it just requires some care, okay? And I'll actually give an example of that, some implementation for that, okay? Let's move on. All right, I think I'm nearing the end here. Oh, this is the end, right? So yeah, so that's basically the usefulness of that. So I thought that I would just finish off this video with some example implementation of the formula that you just saw for the divergence in the polar coordinates. So here we're in Mathematica here, some mathematical software. So what do I do? First, I define the dimension of the space. Then I tell Mathematica the names of my coordinates. Okay. Then I tell it what describes the point on the manifold. Okay, and that's our typical transformation law between our coordinates. And then we have our metric tensor, right? Remember, Gij was d, in this case I'm calling it p, d. In this case I'm calling the coordinates q because I don't want to confuse them with the Cartesian coordinates, but whatever, qi dot dp dqj, this kind of thing, if you remember that. Okay, and I'm saying basically calculate those, put them into a table and simplify it. Okay, and then to calculate the inverse metric, I just take the inverse matrix. I said we can do this in the video, and I showed why. So that's very simple, and again, I get it to simplify it. Then I calculate the Christoffel symbols. So again, so we had gamma, I think I'm using m here, so gamma m ij equals 1/2 g l m times, what was it? It was partial I g l j plus partial j g I l minus partial l g I j. Okay, and I've just implemented that formula in here. So I got to keep track of my summation. So we do a sum here. We have our, actually here I'm summing over k, not l. Doesn't matter, but let's just stay consistent. So we have our g, jk respect to qi, we have our ik respect to qj, and we have the last term here, we have our inverse g over 2. So that's all good. And I make that a table over m, I, and j. So that's the Christoffel symbols. And then I introduce some arbitrary vector, so u, okay, which is allowed to depend on the coordinates, and that's ur of r theta and u theta of r theta, and I'm going to get Mathematica to calculate its divergence, right? So remember, div of u is del k uk, which is equal to, let's be careful here, so del j ui, this was partial j ui plus gamma I j l ul. So if I'm going to switch that to del k uk, all I have to do is switch these guys. Okay, and that's our divergence. And I'm implementing that formula here. Okay, so let's clear this. So So I'm implementing this formula here. So we have, yeah, d ui qi, and then we have the plus. So this is the derivative part. This is the contraction with the gamma part, and we're summing that. It's going to end up being a double summation, as you just saw in the formula. All right. And if we run this code, it gives us, well, it's not clear what these 0 1s and 1 0 means, but in mathematical language, f10 is equal to the derivative with respect to the first argument of f. Okay, so our first argument in this case is r. Okay, so what this basically reads is ur over r plus d theta u theta plus dr ur. And again, when we were talking about normalized versus holonomic bases, we need to be careful here. Okay, so these components are with respect to the holonomic basis, but if I instead want to talk about the components with respect to the normalized basis, all I have to do is go in here and divide, okay, by the size of the unit vector, which is r, right? Because remember, magnitude of e theta was the square root of e theta dot e theta, okay, which is the square root of g theta theta, which is the square root of r squared, which is r. So I just divide this thing, right? Because basically, if I have a big basis vector and a small basis vector, okay, the component with respect to the small basis vector is going to be bigger than the one with respect to the big basis vector, so I need to account for that by dividing by the length. Okay, so once I do that, okay, then we just get the formula that you see in vector calculus books, which is ur over r plus dr ur plus 1 over r, that's that extra factor, d theta u theta. And this is going to be the formula you see in vector calculus texts, right? And the reason why we do all this is because when in differential geometry, the holonomic basis is just easier. It's just easier to work with. All right, that's all. Okay. And I thought I would just show one more thing, trying to keep this whole video under an hour. I thought I would just show one more example calculation that demonstrates the power of this thing we've just introduced. So a formula you might see in vector calculus is that the vector Laplacian of u, all right, so this is in 3 dimensions, the vector Laplacian of u is the same as the gradient of the divergence of u, okay, minus the curl of the curl of u, okay? Or you might see it equivalently written as the curl of u is equal to the vector Laplacian of u minus the gradient of the divergence of u, okay? This form actually makes a little more sense intuitively, but you'll see both. Proving this is a real pain in the butt if you're going to use your traditional, x, y, z, and your, gradient equals dx, dy, dz. It's just a lot of calculation. It's a real pain because this curl of the curl is boy, that's a real pain in the butt. But if you know some tensor calculus and you're willing to consult a little bit of literature, it's actually not that bad, all right? And I'll just demonstrate that quickly. Okay, so the ith component of the curl of u, okay, that's going to be our Levi-Civita tensor, contracted with, right? We're just plugging in the curl of u as our vector. Okay, all right, and then we calculate this curl in here. So it's going to be epsilon I j k del j parentheses. Okay, now epsilon k l m. Alrighty, del j del. Hang on a second. Nope, my bad. Let's see, del L U M. Okay, and then we basically these guys are actually not constant, but because they're basically, these guys are basically functions of the metric, and the metric was the connection was metric compatible. Basically get the covariant derivative of these guys is 0, so we can pull them out. Okay, so this is going to be epsilon I j k epsilon k l m del j del L U M. Okay, and now what we're going to do is we use the anti-symmetry of the Levi-Civita tensor under the symmetry of the Levi-Civita tensor under even permutations. So this, we can move the k 2 spaces back. So this is epsilon k I j epsilon k l m del j del L U M. And now we're going to use a little identity that you'll find in your texts, which is going to be epsilon k I j epsilon k l m, can be written in terms of our generalized Kronecker delta. And then this guy can be written as a determinant of our usual Kronecker deltas, so delta I L, delta I M, delta, let's see, J L and delta J M. Okay, so this is going to be, all right, this determinant, we can work it out. So that's delta I L, delta J M minus delta I M, delta J L times this del J del L U M. So that's going to be delta I L delta J M del J del L U M minus delta I M delta J L del J del L U M. And then what these basically mean is that we can replace L with I and replace M with J, right? That's because this is 0 whenever they're not the same. So this is going to be, okay, del J del I U J minus, okay, replace M with I and L with J, minus del J del J U, wait a second, did I make a mistake here? Yes, del I, yeah, sorry, not del I, UI. And because we are in flat space, we can switch the order of these covariant derivatives. You can't do that in general, but you can in flat space, like R3. So this is going to be del I del J U J minus del J del J U I. And from the previous slides, we recognize this thing as our vector Laplacian, or just our Laplacian, and we recognize this thing as our gradient, and we recognize this thing as the divergence of u. So that is indeed gradient divergence of u minus Laplacian of u. So what do we have? We have the desired formula, curl u equals gradient divergence of u minus Laplacian of u, right? In not a huge amount of calculation. Definitely shorter than if you did it the, let's say, the usual way. Okay, so it looks like we're just coming up on an hour. So I hope this was helpful, at least in some capacity. Once you get practice with it, it's definitely not as hard as it looks. Yeah, that's it. So thank you, and bye-bye.